If we go to DC-Underpinning, we have quite a similar user interface, the same type of icons here at the left side. Again, we have here the standard for the analysis, Eurocode 7 for Germany, for example. And here we have quite a number of basic parameters, for example, which type of earth pressure we want to use for this wall. This might be active or increased active earth pressure or earth pressure at rest. And for example, for increased active, we can define a part of 50% of soil pressure at rest and 50% of active earth pressure. Now, if you compare to the program DC-Pit, where we have foundation pit walls, the input is quite similar, but in this case, we don't only draw the gravity line of the wall, but for these underpinnings, we have a certain shape of the wall. So this might be an arbitrary shape, for example, with a larger thickness here in the soil. There might be some larger thickness here. And if we close this polygon, we have the shape of the wall. And there are two different approaches possible for this program, and it depends on the kind of construction. We might consider a cemented soil mass, which is calculated according to DIN 4093, or a non-reinforced concrete mass, which is calculated according to Eurocode 2. This is quite similar, but depending on the material strength, FMK, we have different reduction factors and different safety factors if we change here the type of standard. So this is a little different use of the factor to be used for the design of the non-reinforced concrete. After the wall, we need the first soil layer. Let's take some sand here, for example. And then we have the wall and the first soil layer. Here again, we may have different soil layers, but in this case, only horizontal ones, because here we have the classic type of earth pressure calculation. And therefore, we only have horizontal soil layers, while in the ground surface, we might have a slope, for example, here. There may be two slopes in the ground which increase the earth pressure on the wall. For this kind of wall, we don't have so many excavation stages, so they're not created automatically like in DC nail. But we start with the anchor layer. Here we want to have an anchor of inclination of 20 degrees, minimum length of 8 meters. The fixed length is 5 meters for this anchor, and the horizontal spacing is 2 meters, for example. And first, this anchor is displayed only in gray, which shows us that this is not yet used because we don't have yet any excavation stage. So we need a first excavation stage here below the first anchor to be able to place the anchor. So in this excavation stage 1, the anchor is not yet used. So this is switched off. And what we can do is to consider the pre-deformation at the position where the anchor will be placed, which means if we have the first excavation stage, we will have some deformation of the wall, and later the anchor is placed at the deformed wall. So this pre-deformation is shifted from the first excavation stage to the second one and considered in the analysis of the wall. By default, the wall is fixed completely in the ground with a full fixing, which may take a force and a bending moment. And if we don't want the full fixing, we can, for example, change the spring constants here. If the spring constant C5 for bending moment is 0, then we have no full fixing. but hinge support, and the wall can turn around this point. So for the first stage, where we don't have an anchor yet, we need the full fixing. So we have empty fields here. And the anchor again is not yet used, but only in the second excavation stage, here E2, for example. Here we use this anchor, and then we don't need a full fixing in the base, for example. So we can enter C5 0. So we have just a support against horizontal deformation. So now this anchor is used in this excavation stage, and we can have concentrated forces on the wall. This could be some building which is supported by this underpinning. Here a load of 200 kilonewton per meter wall, for example. And we can have distributed forces on the ground. And again, if we have the same load case name, these loads are applied at the same time. This might be a live load with a specific safety factor, and these both loads are acting at the same time. Now there also might be a slope here in the excavation pit, on the excavation base. And then we can start the analysis. And this wall is calculated. And then we again can show the graphics as a first overview with a certain scale. And here we have the first excavation stage. And what you can see here in the wall are different lines. We have first the gravity line in red here. This is the center of the wall. We have the width of 2/3 of the shape of the wall, where the load must be transferred in this area. And we see the thrust line where we have the load, which is transferred within the wall. And if this green line is within the blue lines, these loads can be taken by the non-reinforced wall, and we can make a design of this non-reinforced concrete. We have the most important results here. We have the soil pressure. The settlement is calculated in vertical direction. The bearing capacity analysis has a very low utilization, as well the sliding analysis in the base of the wall. And we have the material parameters and the maximum stress and shear stress in this wall. We have the loads, different earth pressures from the ground, from the loads on the ground, the loads on the wall itself, where we also consider that we have quite a large thickness of this wall. So these loads on the wall's back from the wall friction angle delta has a certain eccentricity to the gravity line, and these different loads are shown here and applied to get these section forces of the wall. And what you see is that we have here some changes in inclination. So all these bends and changes in the shape are considered in the calculation to calculate these section forces. Therefore, we have a jump here in the shear force because we have a change in the inclination of the gravity line here. And we have the eccentricity of the wall, of the loads, and the design value of the stress within the load and within the wall. Like in DC-Nail, we have a detailed output here for all our calculation. We have the soil parameters, we have the loads, safety factors, the geometry of the wall, and earth pressure. on the wall. And then we calculated different excavation stages with the passive earth pressure action on the excavated side. We have the loads and the section forces here in the wall, the deformation, the stress in the non-reinforced concrete, and the shear stress within the wall. And then we have different external stability checks, for example, the sliding stability, bearing capacity, with some special options defined in the German standard here. And we have the settlement under the wall. And then the same is done for the second excavation stage. We have a support force here, which is defining the anchor force. And again, deformation, stress, shear stress, sliding stability, bearing capacity, and the settlement, which is below 1 millimeter here. And finally, the stability analysis for the wall, for the anchor, which anchor length is required here to support these forces into the ground.